Okay, in this video I'm going to try to solve this problem from one of the old exams. We're given a signal x of t and we're told that it is known to contain only frequency components which are negative 50 Hertz, 0 Hertz and 50 Hertz. And then we're asked what frequency components will be present in the following signals. So let's look at the first one, x squared of t. So a good way to solve this problem is to actually, like always, try to sketch things as much as possible. So what we are told is x has only 3 frequency components, right? There is some So if it has only 3 frequency components, that means there are 3 impulse functions. One at 0, one at 50 Hertz, and one at 100 Hertz. If we want to work in radians per second, then this is 100 pi and negative 100 pi. So this is x of j omega. And then in part A, we're asked what are the frequency components that are present in x squared of t. How do you think we can solve that?
Find the inverse transform
Of what?
of x of j omega.
You can do that. Yeah, that's a possibility. That can work. But remember, you don't really know these amplitudes. It probably doesn't matter, but that's one possibility. One possibility is to actually write out an expression for x of t and then try to find x of t from there. But another way to do this would be to think of x squared of t as x of t times x of t. So the Fourier transform of x squared should be the convolution of the Fourier transform of x with itself divided by 2 pi. Right? So the Fourier transform of x squared of t is simply 1 over 2 pi times the Fourier transform of x of t convolved with the Fourier transform of x of t. And we know that the Fourier transform of x of t is given by these 3 impulses here. What happens when I convolve this signal with itself? You're going to see something nice. It's pretty easy to do the convolution when you only have impulses. So think about convolving this signal with something that looks like this. I'm going to flip one of the 2 signals and they're all going to overlap. But you don't even have to flip it. Another way to think about it is whenever you convolve with an impulse function, what do? You simply shift it to be centered at that place. So when I do the convolution, I'm going to get a result which looks like this. I'm going to have some component at 0, some at 100 pi, some at 200 pi, negative 200 pi, and negative 100 pi. If that's not clear, you may want to stop the video here for a minute and then think about it. Because convolving with an impulse centered at 100 pi basically means I take this whole thing and then I center it at 100 pi. So when I center this whole function at 100 pi, so this part is going to appear at 0. This part is going to appear at 100 pi, but this part is going to appear at 200 pi. Does that make sense?
Yes.
The same thing when I center it at negative 100 pi, I'm going to get some component at 0, some component at negative 100 pi, some at 200 pi. And then when I center it at 0, I'm going to get things at 0, 100 pi and negative 100 pi. The height or the strength of these impulses I'm drawing is not accurate. We don't really know what the strengths are, but we don't really care. So what would be the answer? Now that we know this is the Fourier transform for x squared of t, what frequency components are present in x squared of t?
Those divided by 2 pi, I guess.
Those divided by 2 pi, which would be, so the answer part A would be negative 100 Hertz, negative 50 Hertz, 0, 50 hertz and 100 hertz. Does that make sense? Okay, now let's think about part B. In part B, y of t is x of t convolved with x of t minus 1. Okay. The Fourier transform of x of t is given here. What is the Fourier transform of x of t minus 1? There's just some e raised to negative j omega times x of j omega, right? So all I'm going to do is I'm going to take my x of j omega and I'm going to multiply it by some function, e to the negative j omega. When I do that, the resulting Fourier transform is still going to be 0 wherever x of j omega was 0. And wherever it was not 0, the value is going to change, but it's still going to be non-zero. So the Fourier transform of x of t minus 1 also has only non-zero components at negative 50 hertz, 0 and 50 hertz. And then I'm convolving x of t with x of t minus 1, which means the Fourier transform of y is the product of the Fourier transform of x and the Fourier transform of x of t minus 1. So I'm going to multiply two functions. Both of them are non-zero only at negative 50 hertz, 0 and 50 hertz. So the answer is going to be simply negative 50 hertz, 0 and 50 hertz.
So the e to the j omega doesn't really matter.
It changes the amplitude.
The strength, right?
Yeah, it changes the strength.
But we don't care about the strength.
But we don't care about the strength because in the problem we are asked only to tell us which frequency components are present in the signal. Okay, now let's look at the third part. That's kind of interesting too. Derivative of x of t. How can we solve that?
J omega times.
Very good. Very good. So we compute the Fourier transform. Fourier transform of y of j omega is j omega times x of j omega. What do we know about x of j omega? X of j omega has non-zero components only at 0, 50 hertz, negative 50 hertz. So what components would be present in y? Same ones, and that's a gotcha. Most people tell me that, but they are not careful when they tell me that. Look at what happens when omega is 0. Multiplying by j omega will kill the 0 frequency component in x of j omega. So the answer is only negative 50 hertz and positive 50 hertz. And part D is y of t is x of t minus 2. What should be the answer for this part? It's very similar to part B, right? That should be the same because just shifting a signal in time should not change any of the frequency components. You should just multiply the Fourier transform by e to the negative j2 omega. So the answer is still negative 50 hertz, 0 and 50 hertz. And finally, y of t is e to the j 1000 pi t times x of t.
That's a change in frequency.
That changes the frequency. So what does that do? That shifts all the frequency components, right?
By 1000 pi?
By 1000 pi. Or in hertz, by 500 hertz. So the answer is, it's going to have 450 hertz, 0 and 550 hertz. That's the final answer.